So we had the Bohr model now, and it worked great for hydrogen. Unfortunately, as soon as you moved away from hydrogen gas, the Bohr model didn't work anymore. So as soon as you look at a neon line spectrum, the Bohr model does not provide a way to predict the line spectrum at all. And thus, it really came into question whether the Bohr model was an accurate description of atoms at the subatomic level. And so really it became clear that electrons do not simply sit on orbits around the nucleus as described in the Bohr model. So the Bohr model is not an actual correct description of the atom at the subatomic level. However, two of Bohr's postulates remain true, and that's part of science. Many things that we propose are incorrect or found to be incorrect, but often it's this slow progression in knowledge. So Bohr didn't have the whole picture right, but he did have two things right. The first of those being that electrons do only exist in discrete energy levels. They can't just exist anywhere in the atom. They do exist in discrete energy levels and discrete areas or space around the nucleus. And then second, electrons can transition between these levels, and energy is involved in the transitions between levels. It takes energy to go to a higher energy level. You release energy going from a high energy level to a lower energy level, and that process of releasing energy does explain the line spectra, even if Bohr's model doesn't explain the locations of more complicated line spectra. What's not true from the Bohr model, however, is the position of the electrons around the nucleus. They do not exist on simple orbital tracks around the nucleus. And what actually is even a little bit more complicated is right around this time, and this is all happening in the very early 1900s, so 1900 to 1920 or 1930, there was an explosion in our understanding of the atom and the subatomic particles in the quantum realm. And Louis de Broglie was looking at electrons and noticed, look, we have been talking about light, and we've found out that light does not exist just as a wave. It exists also as a particle. It's a small, extraordinarily small particle energy packet known as a photon. Well, an electron is an extraordinarily small particle. Is it possible that perhaps it doesn't behave simply as a particle, but maybe as a wave? And he showed this actually to be true. Electron doesn't behave simply as a discrete particle. It's not like just a simple bead. It actually behaves also as a wave on the subatomic level. And so just like light waves that you can split using a prism to show the different wavelengths of light, you can actually also split an electron wave in a similar manner. So after de Broglie, and these are all steps in the process of our knowledge, but after de Broglie, and again, all of this is happening at kind of the same time, there's another scientist, Werner Karl Heisenberg from Germany, and he was also studying the electron and said, after a bunch of study, he noted something that's become kind of famous in terms of his uncertainty principle, which is simply that although we may be able to know the position of an electron, and we may also be able to separately measure the speed of an electron, we cannot know both the exact position and the exact speed of an electron at any given time. We can't know both things at the same time. We can know one. As we become more accurate with one, we become less accurate with the other. So, okay, what can we know then? If we can't know the exact location of an electron, and we can't, at least not at any, and we can't know its speed at the same time, and both of those are important factors in terms of the physics of the atom, what can we know? Well, we can know something, this is a description known as a wave function, which is just a mathematical description of electrons in atoms. These wave functions are complicated, far beyond the scope of this course or many undergraduate courses. But if you take the wave function, that's just a mathematical description of the electron, and the square of the wave function happens to be something known as the probability density. This is just a map of the probability of finding an electron within that shape. It's also known as the electron density. So if we look at a probability density map here, you can see that all of the different spots represent probability. And the places where there's a high density of dots indicates that there's a high probability of finding an electron in this region. Since we can't know the exact position and speed at any given time, we can though have a probability for where the electron will be at any given time. And so we can then draw these type of maps. But one thing that's useful from this is that if we draw some shape that contains 90% of the probability density. So 9 times out of 10, the electron's gonna be in that shape. We refer to that shape as being an orbital. It's a 3-dimensional shape around the atom. We refer to that shape as being an orbital. Now, there are many types of orbitals, and every atom has many, many types of orbitals, and each orbital exists at discrete energy levels, similar to the Bohr model, but now it's not circular orbits around a nucleus. It's now shapes that contain a 90% or greater probability of finding an electron in that space. And those shapes can take varying sizes. We'll get to that later. But each orbital can be described using certain descriptors. So they're not simple circular orbits. How do we describe them? We use 4 descriptors known as quantum numbers. And each of these quantum numbers describes something specific about the orbital. Remember, the orbital is just a shape that contains a probability density of finding an electron in that shape. So the first quantum number is simply the principal quantum number, and this is the same as for Bohr. This simply describes the energy level or the energy shell for that orbital. And it has to be a positive integer value. It can be, anything greater than 0, but it has to be an integer value. And it describes not just the energy, but describes the distance away from the nucleus, and thus relates to the energy of the orbital. The second quantum number is known as the azimuthal quantum number. It's given the symbol L, and it's also known as the angular momentum quantum number. This one may not make a ton of sense, so let's see, what is this one describing? This defines the shape of the orbital. And this ranges in integer values from 0 up to n-1. We'll get to some more of that in a little bit. So if the principal quantum number tells you the energy of the orbital, the azimuthal quantum number tells you the shape. And then orbitals themselves are designated by letters depending on what the value of the azimuthal quantum number is. So if L is 0, then we call it an s orbital. If it's 1, we call it a p orbital, 2 is a d orbital, 3 is an f orbital, I think 4 is a g orbital. But these letters now are designated to the different shapes of orbitals. And each of these shapes of orbitals are designated as being subshells. Now, sometimes you can have more than one orbital in a subshell, and we'll get to that in a moment. And that's kind of where the magnetic quantum number comes in. This is given the symbol m sub L. And this defines the 3-dimensional orientation of an orbital. So an orbital may have a particular shape, but how is it oriented in three-dimensional space around the nucleus? And that's where the magnetic quantum number comes in. And that's why also for any given value of L, where you would then have some letter associated to it, there can sometimes be multiple orbitals because they may have different values of m sub L, which means they have different orientations in three-dimensional space around the nucleus. So m sub L can be an integer value that ranges from negative L to positive L. Those are the possibilities, and describe how many orbitals there are. And then there's finally the spin magnetic quantum number. This is m sub s. This describes not the orbital itself. It describes the electron inside the orbital. And it describes the, quote, spin of an electron in the orbital. Electrons, as we'll talk about later, can only have two spin options. They can either be spin up or spin down, and we designate those as being +1/2 or -1/2. But that describes the electron itself inside the orbital. So the first three numbers describe the orbital itself. So let's go through some more examples. What does this look like? How does this describe many orbitals? Well, let's just look at the possibilities at each energy level. So if we are at the n = 1 energy level, that's the very fundamental energy level, the possible values of L have to be range from 0 to n-1. Well, n-1 is 0, so the only possible value of L is 0. And that would be an s orbital. We designate anything with an L = 0 to be s. And then values of m sub L, well, they range from negative L to positive L. Well, we're at 0. L is 0, so the only possible value of L is 0. M sub L is 0. And remember that m sub L defines the three-dimensional orientation. This means that at n = 1, there's only one possible orbital at that energy value, because there's only one possible shape, the L = 0 or the s orbital, and there's only one possible three-dimensional orientation in space, so there can only be one orbital. However, as we move to the second energy level now, n = 2, now the possible values for L, which describes the shape of the orbital, I have two different possibilities. L ranges from 0 to n-1, so it could still be 0, or it could be 1. If it's 0, then it's an s orbital, and the only possible or three-dimensional orientation in space is just one possible orientation. So there's just one orbital with this s designation. But if L is 2, we then designate that as being a p orbital. But now, in terms of my three-dimensional orientation in space, there's three different options, because I can have m sub L being, it ranges from positive to negative L in integer values. So it could be 1, 0, or -1. That's three different three-dimensional orientations in space. So for each of those designations, I will have three different orbitals. I have one where, so n = 2, L = 1, but then I'll have an orbital where m sub L is 1, so that's one three-dimensional orientation in space. I'll have a different orbital where m sub L = 0, and I'll have a third orbital where m sub L = -1, all oriented differently in space. So in the total shell, then in the subshell, there are 3 orbitals. In the total shell, there are 4 orbitals in that energy level or energy shell. As we move out to a larger energy shell, so n = 3 now I have even more expanded possibilities. The azimuthal quantum number, which defines the shape, could be 0, 1, or 2, which would be s, p, or d orbital designations. And then we'd already gone through the s and the p designations, but for the d, now I have 5 possible three-dimensional orientations in space for these shapes. And that could be where m sub L is 2, 1, 0, -1, or -2. So I'm going to have 5 different orbitals. Each one has one of those orientations in space. And so the d subshell has 5 orbitals, the p subshell has 3 orbitals, the s subshell has 1 orbital. And so this entire shell has 9 orbitals in it. As you keep going, you imagine that that process continues. You have the f orbitals, and we can just, by analogy, extend this out. And so when we see the many lines from a neon line spectrum, what we're seeing is electrons transitioning between 2 of these many different orbitals. We have many different orbital options here. And for neon, when we see the many different line spectra, what we're seeing is electrons jumping from between multiple of the different energy, between multiple of the different orbitals. Each orbital's got its own energy, and so we have all of these different energies then that correspond to all of these different wavelengths, but it still occurs at discrete wavelengths, and so we have this line spectrum. So then, what are these shapes, what do these orbitals look like? Hopefully you're not too confused at this point. What do these orbitals look like? Well, let's just take a quick look. First case, when the azimuthal quantum number is 0, the s orbital, that is spherical. S for spherical, essentially. It's one way to remember it. And it's simply a ball around the nucleus. In terms of, remember that our orbital is really just a map of the electron density. It's a shape containing the probability of finding an electron in that shape. And so m sub l is 0. There's only one possible 3-dimensional orientation in space, and that makes sense for a sphere. There's really only one possible way to orient a sphere in 3D, because no matter how you spin it, it looks the same. And we'll have an s orbital at each energy level, and they simply get larger as the energy level increases. What about the L equals 1? This is the p orbitals. Well, they have a very different shape. So the p orbital shape is more like a dumbbell that you would lift in a gym. So it looks a little bit more like this. There's actually 0 probability of finding an electron at the nucleus, but then there's these 2 spaces on either side of the nucleus where you would find the electron. And it could exist on either side of the nucleus. Both of those are considered to be 1 orbital. And there's 3 different options here, because m sub l could be -1, 0, or 1. So I have 3 different orbitals, and those 3 different orbitals are simply oriented along the 3 different axes in space. So along the z-axis, the x-axis, and the y-axis. And we designate them as being, which one, if we need to, we designate them as being pz, px, or py. The last case is when I have L equals 2. So these are the d orbitals. Now, the d orbitals have actually not one uniform shape for all of them. There's 4 that look the same, and then 1 that's weird looking. So, and that accounts for the 5 different possibilities, the 5 different orientations in space, which we have from the m sub l values. So here you can see they mostly look like clover shapes, except for the 1 dz squared, and you do not have to remember the designations of these different orbitals. Just note that there's 5 different orbitals for the d orbitals. Now, when it comes to energy, sometimes it's helpful to arrange these different orbitals by their energies in order of their increasing energy. So what we'll see here is, if we start here at the bottom, if energy increases as we go up, then we'll always start at an energy level generally. So we start at 1, and the only possible orbital in the n equals 1 energy level is the s orbital. So you have the 1s orbital. But then in the n equals 2 energy level, you have the s and the p orbitals. Now, s orbitals are always lower in energy than the p orbitals. But we'll notice here, if these boxes represent the different orbitals, that all 3 of the different p orbitals are all at the same energy. And that is true. Anytime that you have multiple of the same exact type of orbital, where the only difference is just their three-dimensional orientation space, we refer to those as being degenerate, meaning they have the same energy. So the three orbitals that are in these, the three different p orbitals that we have, all have the same energy. Then we go up to the 3s and the 3p, and the 3ds are even higher in energy than the p's. So s is always lowest in energy, then p, and then d's are higher in energy than the s. And one thing we have to pay attention to, though, is that there is one little complication. So normally you would just say, okay, well, s, p, you know, s, if there's any s's, well, in the first, there's always an s orbital, but there's not always a p or a d or an f orbital. That has to do with the p's appear in the second energy level, the d's appear in the third energy level, the f's appear in the fourth energy level. And normally s is lowest, then p, then d, then f. But when it comes to the overall energy levels, it turns out that the 4s orbital is actually slightly, just only a little bit, slightly lower in energy than the d orbitals from the previous energy level. So as we get, when the d orbitals appear, we just note that we insert them between the s and p orbitals of the next energy level. If it's helpful to have it written out, it's just in terms of increasing energy, it's 1s, 2s, 2p, 3s, 3p, 4s, 4d, 4p, 5s, 4d, etc. And that's a description then of the atom and atomic theory in a little bit more detail, albeit a little bit more complicated.